question 18 here, and hopefully that'll get you through the rest of the practice exams. These questions, some of them are a little bit harder than I would be expecting, but if you're ready for these, then you'll be ready for pretty much everything they throw at you. So that's a good way to look at it. Beaker of water is removed from heat and placed in a room at 22 degrees. The temperature falls from 90 to 70 in 5 minutes, and then they give you Newton's law of cooling, where capital T is the temperature, little t is the time in minutes, and that's what we've got to go ahead and do. So you'll notice that the 22, that's often labelled the TS for the temperature of the surrounds. But in this case, they give you the equation. You're not expected to know Newton's law of cooling, so that's reasonable. So when I start to try and do this, the derivative of the temperature in terms of time equals negative K T minus 22. And if I integrate it in terms of T, I could get, in terms of little t, I could get capital T on that side, but I can't. There's no little t on the right-hand side. It's a little bit annoying. So what we want to do is something called separation of variables. We're going to break this fraction up. I'm going to keep the dt capital T that's in the numerator on top, but I'm going to multiply each side by d little t, which means d little t is going to turn up here on the right. And because my capital T is on the left-hand side, I want to make sure I get this expression, the t minus 22, on the other side. And in order to do that, I need to divide by t minus 22, which means it's going to cancel on this right-hand side, and it's going to end up as 1 over t minus 22 on the left. The k, I'm just going to keep where it is because I think it's easier if you keep it on that right-hand side. You could move it across, and it still works. I just think it's a little bit more complicated. So we break up this fraction, keep the capital T that's in the numerator on the left, take the little dt over to the right, that's multiplying each side by that, and then I'm going to divide by t minus 22, which sends it over to the left-hand side. I can now integrate these expressions. The left-hand side I'm integrating in terms of capital T, the right-hand side in terms of little t. So when I've got 1 over something, that comes from the natural log of t minus 22 in this case. And on the right-hand side, well, k is just a constant, so this is negative k, and if I add 1 to the power of t to the 0, I get t to the power of 1, or just negative kt. Because there's a constant of integration on both sides, I could always subtract them or whatever, so I really just need to add the c on one side. And if you trust me, it's easier if you just keep it on the right there. Then it says determine the temperature of the water in 15 minutes. They give me some information before that, though. Here it is. The temperature falls from 90 degrees to 70 degrees in 5 minutes. So that's giving me 2 bits of information. When little t equals 0, capital T is 90. So I can have an equation, the natural log of 90 minus 22 equals negative k times 0 plus c. And if I just simplify 90 minus 22, I believe I get 68. Log of 68 must equal c. And then they give me another bit of information. When t equals 5, time equals 5, the temperature is equal to 70. So now I can write the natural log of 70 minus 22 equals negative k times 5 minutes. And we have our natural log of 68 on the right-hand side. And we can now rearrange this to solve for k, or it's a calculator question. You can just use solve_n to get to that answer. Now, I don't have a calculator on me, but actually I do. I'm using my computer, not my iPad. Let's actually do it. That would be helpful of me, wouldn't it? Now, I think it's only sharing a window, so you might not be able to see what's on my calculator screen here. I'll see if I can change those settings. Let's have a look. Okay, hopefully this is continuing on from what we did. Doesn't that look fancy? We don't need that. We're up to our calculator there. And if I get back to this is where we were. I can use solven on that expression to try and find the value of k. So if I bring up my calculator, just in the run matrix, is it options, calculate, solven, and we had the natural log 70 minus 22. What's that? 48. You could just type in 70 minus 22. They could have been. Let's do that. 70 minus 22 equals, no, equals negative, and I'll have to make it 5x, negative 5. And make sure I use the x off the calculator button. And then we had plus the natural log of 68. Making sure I got that right. Yep. And now we can just press execute there, and it's going to figure out the value is 0.0696. So around 0.070 should be good enough. Okay, so we've got our k value. So now we've got our actual equation, the natural log of t minus 22. You can see I'm in the habit of doing absolute value, but in methods, they'll only ever give you ones where it's true. So you can just put brackets there. And that's going to equal negative 0.07. I'm going to keep writing the 0, even though it doesn't affect my calculations, just to remind the marker that I know what I was doing, and I've rounded to 3 significant figures there. Plus log 68. You could, of course, store that value in on your calculator as well. We've now got our equation. They've asked me to find where T is the temperature, determine the temperature of the water 15 minutes after it was placed in the room. So now I'm just going to let little t equal 15. And I'm going to use solven to find capital T. I'm just going to write using GDC. So I'm going to basically have the same thing that I had up here. I can even go in and use that. This time, capital T is my variable, so that's the x minus 20. Oh, I've got to remember to use the one on the calculator. X minus 22 equals negative 5. The 5 I need to keep. I was trying to delete the x there. I don't know what I've just done. That's all right. We're still there. And the number's still conveniently written there for me, 0.06966133885. I mean, you don't need to go to that level of accuracy. It's probably still going to work fine. But seeing as though it was written out there directly underneath, hopefully that will sort me out. So now I can just do that. And this time it's going to solve for the capital T temperature, because that's what my x is. So when I press exit, T equals 70. What did I do? Oh, I've got... that was 5 minutes. We needed 15 minutes. I thought that was wrong. There we go. So we do it again. Press execute. And this time we'll get it right. You know I can't be trusted on the calculator. It's always good just to double check what you're doing. But therefore the temperature is approximately equal to 0.92 degrees. And there you've got your temperature. So it's a little bit tricky separating the variables up here. It could appear, it has appeared in the past, but it's a little bit technical doing that. It's something that we'd expect more in specialist. But if you can follow that through, and most people seem to be able to, that's worked fine for them. So I'm sure you can do it too. Here I've got a racing boat is traveling at 20 meters per second when its parachute is released. After release, the acceleration is modeled by that equation. So again, it's an equation where I've got the derivative, so I want to go ahead and find the other expression. Again, this one's interesting because the derivative of v in terms of t, rather than equation in terms of t like we'd usually expect, it's actually got the equation in terms of v, which is unusual. So we need to do the same trick that we did in the last one. So I want to get my v on the other side with my dv, so I'm going to make it 1 over 20 minus V. And my dV stays there. And that's going to equal, well, if I divide by that, I'm just left with 1. And then I multiply by dt, so the dt's on the right-hand side. Integrate each side. And so this is going to be just t, because the integral of 1 in terms of t is t. I'm going to add my c. And on this side, I've got the log of 20 minus v. But in this case, because it's -1 is the coefficient of that v, I've got to divide by -1. Well, that's just the same as putting a negative out the front. So remember, for our log laws, when I've got the log of ax plus b, when I've got 1 over ax plus b, and I'm integrating that, that becomes 1 over a, natural log of ax plus b. And I've put my c on the right-hand side rather than the left-hand side because I only need it on one side. That's pretty good. Determine the velocity of the boat after 6 seconds and comment on the reasonableness. So if I let t equals, well, I've got an issue here that I don't know what c is at the moment. When t equals 0, I guess I can find out. And this is where we come up with something very interesting. If I try and substitute this in at this point, the log of 0 does not have a solution. And this is where AI has tried to write the question, and it's made one that doesn't really work very nicely. We can't just substitute in at this point. It doesn't give us values that work because I can't find the log of 0. What's actually happened is because the racing boat is traveling at 20 meters per second, and then its acceleration is 20 minus whatever the velocity was at the time, well, the initial velocity was 20. That means its rate of change was 0. It wasn't accelerating the whole time, and it didn't. We were expecting negative acceleration because a parachute would slow it down. But this didn't slow it down at all. So determine the velocity boat after 6 seconds. It's still going to be 20 meters per second. This is not a reasonable model because the parachute didn't slow the speedboat down. I really just wanted to show you that first little bit again, how we get to there. We could, even though this question doesn't work, so you don't need to panic too much about this one, I could try and continue to solve this. I could make this the log of 20 minus v equals negative t. And you could go minus c, or I'm just going to go plus c1 when I'm multiplied by -1. And then I can use my definition of a log. So this is base e, so I can go, this is e to the power of negative t plus c1. I could then subtract the 20, so I've got negative v equals e to the negative t plus c1 minus 20, then multiply through by -1 again. V equals 20 minus e to the negative t plus c1. And that could be my equation. And now I could substitute in let v equal 20 when t equals 0. And we have that same problem again here where 20 is equal to 20 minus e to the power of something, but this e to the power of something has to equal 0, and we know from our exponential graphs that's not possible. So again, this model would be unreasonable. The initial bit, though, how you can separate that derivative, the dv and dt, into two separate bits, that's an important bit to at least understand can happen. But again, not probably the focus of what we're going to be doing. Let's have a look at this next one. A metal tube has an inner radius of 2 centimeters and an outer radius of 6 centimeters. So it's quite a thick little tube, this one. And so pretend that's perfectly concentric. So 2 centimeters and 6 centimeters. And the temperature within the metal is determined by the length of the radius. The radius is how far from the center of the circle out, and radius can obviously go all the way to the outer bit We'll start at the inner bit. The inner surface, let's write out the rule. The temperature in terms of the radius is A times the natural log of whatever the radius is plus B.